You will soon be able to 4x your context window. And no, I'm not kidding. That is the promise of TurboQuant, a brand new compression algorithm from Google. If you spend any time building apps with AI, or just use Claude or ChatGPT to its limit by using huge prompts, you know the pain of hitting that memory wall. The AI starts forgetting about your instructions. It hallucinates and the output becomes unusable. But this new update could make your models 4 times more powerful by expanding what they can actually remember at once. In this video, we're gonna break down the exact math behind how this compression algorithm works, how it fixes the biggest bottleneck in AI right now, and when you can actually start using it in your workflow. To understand why AI sucks at remembering long instructions, you have to understand the concept called key value cache, or KV cache in short. When you feed a prompt into an LLM, it doesn't just read and magically understand what that is. For every single token, the model's attention mechanism generates multidimensional mathematical vectors, a key and a value. Keys act like labels or indices. Values hold the semantic meaning. The models store this in a short-term memory, the KV cache, so that it doesn't have to recalculate the entire conversation for every single word that it generates. The problem with this KV cache is that it scales linearly. It grows with the context length, the number of layers in the model, and the number of attention heads. And historically, it stores all of this in a 16-bit floating point precision. So if you dump something like an entire code base, a PRD, or all the edge cases into the model, the KV cache blows up. For a 80 billion parameter model with a 32,000 context window, the KV cache alone eats up 5 GB of VRAM. For a 70 billion model, it can eat up to 80 gigabytes. The model weights aren't the problem, the KV cache is. When the GPU runs out of this VRAM, it starts swapping to slower system memory. The system crawls to a halt. The AI forgets your core architecture of your app, and the output becomes unusable. TurboQuant is an algorithm developed by Google Research which attacks this KV cache directly. It compresses the cache down to just 3 bits per value, a massive 6 times reduction in memory with literally zero accuracy cost on long context benchmarks. It is a 2-stage mathematical pipeline. The first stage is the PolarQuant. Standard quantization tries to compress these vectors from 16-bit to 4-bit integers. But there's a catch. To decompress this data later, traditional methods require metadata for every small block of numbers. At 3-bit compression, this metadata takes so much space that it totally defeats the purpose of the compression in the first place. PolarQuant fixes this by completely changing the geometry. Instead of looking at the data in XYZ axis, the standard Cartesian plane, it applies a random mathematical rotation that converts these vectors into polar coordinates, a radius and an angle. Because of the rotation, the distribution of these angles becomes normalized and predictable. Since the AI knows what the structure, what the shape of this data is, it can start compressing it aggressively without needing to store any metadata or scaling factors. This leads us into the second stage of the compression algorithm. Even with PolarQuant, the 3-bit compression leaves behind a residual mathematical error. And in AI, mathematical errors build up to become hallucinations. To fix this, PolarQuant takes the leftover error and applies a 1-bit QGL transform. LLMs figure out what words are important by calculating attention scores, which is just a dot product of the key and the value in the vector. Then QGL projects the remaining or the leftover errors into small dimensional spaces and squashes it down to a single bit, either +1 or -1. Now, after all this talk, what is the actual real world impact of this whole compression algorithm? This isn't just a slight optimization. It fundamentally changes what hardware can run what models. Even my phone can run models now. A 6 times memory reduction means that a 128K context window can now theoretically be close to 768K on the exact same GPU setup. You can feed it entire code bases without it choking. And because the KV cache is now 6 times smaller, it all the time stays in the VRAM itself, which means it is a lot faster to access this KV cache, making the model hallucinate less and follow your instructions better, even the ones that you told it at the beginning of the whole context window when you actually started talking to it. But is it just theoretical, or can we actually use it right now? The reality check is that TurboQuant is a brand new compression algorithm. It's not like a patch or a switch in your Claude or ChatGPT interface which you can just toggle. It will take some time for these companies to actually adopt this compression algorithm and provide the benefits of it to users like you and me. But the good news is that it doesn't depend on the data. So we don't really have to pre-train or train the models again. We can just implement it in an existing workflow and it will compress the context window, because it is just a mathematical equation at the end of the day. In fact, the open source community has already created a package for this. You can install it by using pip install TurboQuant. For average users who are relying on web UIs or APIs of the big companies Anthropic or OpenAI, we have to wait for the providers to actually bake this mathematics into their workflows. But the blueprint is out there. The era of constantly fighting with the context window is officially ending.